Before we get to the specific questions, there are some general things I just want to share to make sure we're on the same page when it comes to directions. Now, I've mentioned already we don't want bald answers, so make sure you don't have any of those. And one of the ways you make sure you don't have bald answers is by actually showing or justifying your work. Now, I do want you to be careful because a lot of times we may use the words justification and interpretation interchangeably. And in this specific case, that's not what's going to happen. Justification is where you show why your answer is correct. Interpretation is explaining your answer, well, what your answer means for the particular problem you've completed. So sometimes you have to do both, but definitely you don't want to justify when you mean to interpret or interpret when you mean to justify. Without further ado, let's talk here. So this was the first one. I hope this one was pretty straightforward. You read the table, you got the value at 0. Notice that the value was 0, checked your definition, said moving left. Okay, moving on. This next one, not as straightforward, and a wonderful chance to review once again the intermediate value theorem, because I don't know if you've noticed this, it keeps coming up. I've written it a little bit differently here to give you a fresh new perspective, but I've still done the same things with the intermediate value theorem. So I've answered the question, yes. Okay, what else have I done? I've shown that the values at 0 and 5 are -3 and 3 respectively. So I know that the value that I want for V of t is between those. And I've explained that I knew V of t is continuous, which means the IVT applies. And then I've got my conclusion on here. Please make sure your conclusion says there must exist at least one t value. Now, let's suppose this wasn't possible. One thing that I do want to caution you against, and it's been a while since we talked about the intermediate value theorem, just because we might not have this kind of bracket coverage, like let's say there's no values of V that are negative, all the values of V are positive. That doesn't mean that we never reach 0. It means we may not reach 0. So the opposite of the intermediate value theorem, can't find a value, doesn't mean the value doesn't exist. It means that it may not exist. Anyway, moving on to number 3, another review. Hey, approximating the instantaneous rate of change of a thing using a table. So we choose 12 and 8 because those are the closest values to 10. Make sure your units are correct. Observe the units in the numerator for velocity are meters per minute. When you do meters per minute divided by minutes, which is what 12 and 8 share for units, you have meters per minute, which you can also express as meters per minute squared. Please make sure you do use the double tilde for approximation. And then the interpretation. Notice how I said when, notice how I said what's going on, and I've got the correct units. There's another way we could interpret this, and that's because of the language that we're using. Remember that V prime of 10 is A of 10. So we have a negative acceleration. A negative acceleration means two things. It means, first of all, the velocity is decreasing, and second of all, and you may not have made this connection, but I said acceleration ditto velocity. Well, if the velocity is negative, then the particle is moving left. If the acceleration is negative, then the acceleration is also to the left. Notice how I didn't say anything about speeding up and slowing down. That is purposeful because that is coming later. So hopefully that was something that was new for all of you, that were you getting something out of me going over answers. So we're not going to talk about number 4 yet. Number 4 is going to be coming up in the next unit, wherein we discuss Rolle's theorem and the mean value theorem, bringing our total of calculus theorems to 3 out of 5. So if you couldn't do number 4, that's okay. You just need to figure out how to show that you could get a slope of 0. And there's two theorems that prove that. And they work very, very similarly to the intermediate value theorem. Moving on to the second example. First one is very, very similar to the first one in the first example. The difference here is we read the table. And when we read the table, we notice that the velocity is above the t-axis. So the velocity is positive, we're moving to the right. Number 2, also very similar to number 2 in example 1, but I've done this a little differently. Notice how I wrote this sentence first. I'd like to challenge you when you're doing these motion questions to write out what it is you need to show, because that's going to be an excellent way for you to review your important and relevant vocabulary. Think about how much class time we spent setting up the vocabulary here. That took forever, didn't it? Think about how much less class time we have than I would want. I'm telling you how important that is by the amount of direct one-on-one time, well, not one-on-one, but you know what I mean, direct time looking at that. That's because without those definitions firmly up here, we're going to have a huge struggle doing motion. So you'll notice me use this technique a lot. So I have both used my definition and justified my answer to say from 5 to 9. Also, real quick, in case I forget to mention it later, we do want to make sure that we are using open intervals. You could use a half open, half closed here, but it's just better generally to do always open. So number 3, notice again how I have used a description I didn't necessarily need. Acceleration is the derivative or slope of v of t. I didn't need to say that here. I chose to say that to communicate to you and also to help you practice, because we're practicing our vocabulary. I could do the same thing as that sentence right here by saying a of t equals v prime of t. And then I have a really important observation I'd like to make for you. Do not get addicted to doing calculations to show what you want. If we go back to the definitions for velocity and acceleration, and for that matter, position, there are 2 significant things. There is the value and there is the sign of that value. We are in a land of vectors, which means we have magnitude, or how far, how big, how whatever, as well as direction. So like position, a negative sign means to the left or down if you're moving up and down. Same thing for velocity. A negative velocity means moving left. A negative acceleration means accelerating left, not speeding up, accelerating. So if you took time to calculate this value, that's okay. Just know that you don't need to calculate it. All we need really is the sign. That's all we needed to answer that. Number 4 is typically where we have problems. I would like to remind you again, average acceleration is the average change in velocity. So I found an average acceleration using velocity values. Also, the units make sense. The numerators units are feet per second. The denominators units are second. So it's feet per second, or feet per second squared, which is what we expect for units of acceleration. Number 5, I'm not going to be talking about because we would need the mean value theorem here. Number 6, however, I'm going to let you marinate in for a little bit. And then we draw our attention to number 3. So number 3 was an equation, and it also had the most difficult questions, I think. But the equation makes it a little bit more accessible. So number 1 is the same number 1 as example 1 and example 2. What's different this time is I have to actually get the velocity by taking the derivative of position. Why did I do that? Because I made this connection. And this connection comes from my recollection of the definitions we spent so much class time going over. So if you're moving right or left, you're talking about velocity being positive or negative, which means I need velocity, which is the first derivative of position. Then if I substitute 0 in, I get 9 units here are undeclared. So I didn't worry about them too much, but I probably would normally. Since the velocity is positive, we're moving to the right again. Okay. Number 2, I started out in a similar fashion. I said velocity increasing or decreasing means I need to show the acceleration is positive or negative. Why acceleration, you may wonder? Because acceleration is the first derivative of velocity. And we remember from earlier in the class that when a function is increasing, its derivative must be positive. Likewise, decreasing and negative, and the reverse is true. If a function's derivative is negative, the function is decreasing. So I took the derivative of v of t. Notice how I've marked it as a of t equals v prime of t. So I've introduced a new function, a of t. I've connected it to v prime of t. That's where I get 6t minus 12 from. This is just me noting to you that you could have included, this is also x double prime of t. It's not necessary here, but you could have. And then I did something very similar in number 2 to what I did for number 1. But this time I use the acceleration. Okay. Oh, I forgot to mention something, sorry. I didn't mean to go on to number 3 here, but I did mentally without finishing my thought, excuse me. So I already mentioned that acceleration being negative because it's the derivative of velocity, means velocity is decreasing. Acceleration being negative also means acceleration to the left. Sorry about that. Doing it out of order. Okay, so again, I challenged myself to use my vocabulary. Moving left means the velocity is negative. So I did this. And you probably are looking at this and you're like, why did you do that, Mr. Lepkowski? Because what does this have to do with the velocity being negative? You've taken the velocity, you've set it equal to 0, you've solved for t and said t is 1 and 3. How does that help? Well, that helps by following a chain of logic that you may or may not have figured out with your team that I would like to go through with you. So why did I do this? Well, I did this because there are only 3 possible things the velocity, well, I guess 4, but one of them doesn't apply here because of the nature of the function being continuous and differentiable because it's polynomial. The velocity can only be positive, negative, or 0. Those are the only possible outputs for this kind of function. Yes? Okay. I'm only interested in the negative ones, right? That's all I'm interested in. But if I know where the function is positive and 0, then I'm also going to know where the function is negative. Okay, so how does that help? I now know when the function is positive, negatives, and 0. Actually, I don't know any of that. I only know when the function is at 0. Well, there's another piece to that. Here it is. Because the function is continuous, its graph will be wholly or entirely positive or negative if it isn't 0. There's no funny business going on. This is a polynomial. Yes, it's a parabola. We know what the graph of a parabola looks like, but we can use that same logic to any polynomial. It's going to look like some kind of goofy thing that's got maybe like parabola pieces to it. It's got to behave like this because of the function. So the function's continuous, which means if we determine the direction changes or points of rest, that is where the velocity is 0, we know that in between that, there's only 2 possibilities. If you're not 0, you're moving right or you're moving left. So that was my logic for doing this. So to finish up here, I wrote my workout like this. V of t less than 0 means the particle is moving left. Oh, those weren't supposed to be there yet. Sorry for confusing you. I made a number line. And all I'm interested in here is the sign part of the velocity. That's all I care about. I don't care about what the number is for the velocity. All I care about is less than 0. So I know at t equals 1 and t equals 3, the velocity is 0, right? The velocity is 0 here. So the question is, what happens before 1, between 1 and 3, and after 3? This is either positive or negative. This is either positive or negative. This is either positive or negative. And I could look at the graph. I could have done that. Some of you might have. But I could also choose a representative value, like 0. Substitute that in to the velocity and determine that the velocity is positive. And then I could choose a value between 1 and 3. Now, I'd probably suggest 2, but it doesn't actually matter. Any value is going to do. I could do 1.98. 1.98 substituted into the velocity results in a negative value. So I know that every single velocity value from 1 to 3 is negative because this is a continuous function. And then I repeat the process. I choose a value bigger than 3, like 11 pi. Doesn't have to be 11 pi. It could be anything bigger than 3, like 4. It's also positive. So I know that velocity is positive, velocity is positive, velocity is negative. So the interval from 1 to 3, the velocity is negative, the particle is moving left. This is the last one. I will let you marinate in that for a bit. So finishing up after marinating on this for a little while, I tried to be really clear about what I wrote down. So I connected number 4 back to the definition where we talked about how total distance means finding stopping points. The reason why we need to find stopping points is because similar to what we did in number 3, that tells us that the velocity or motion is left or right in between those values. Has to be. So from part 3, when I determined 1 and 3, I knew that I had from 0 to 1 and 1 to 3 and 3 to 5, those 3 distinct intervals. So what I did was I found my position by substituting into the position function. So that's the original x equation. I substituted in 1 or 0, 1, 3, and 5, and then I subtracted them. And I noticed something really interesting. I noticed that the position at 1 was 15 and the position at 0 was 11. So to go from 11 to 15, that was 4 units. That's moving right, right? You have to move right to go from 11 to 15 on the horizontal axis. And that matched what I said about the velocity. The velocity from 0 to 1, remember, we said was positive. Okay. Then I said, okay, from 1 to 3, what's going on? Well, when I'm at 1, like I said, I was already at 11. At 3, I get back to 15. So I've moved left 4, which matches my negative velocity. And then from 3 to 5, I've moved right 20. So if I add all of those together, I have a distance right of 4, a distance left of 4, a distance right of 20, and I get a total distance of 28. And once we get into the second half of class with integration, we'll have a different way of doing this that some people say is easier, some people say is not. Whew, man, we did hard work today with that.